a DST project, sponsored project. He is a member of IEEE and ACM. I welcome our speaker to proceed with the further session. Thank you.
Yeah, thank you very much for introducing me. So first of all, I would like to convey my thanks to all the organizers for organizing this event and inviting me to deliver some of the interesting talk on the IoT. So yeah, my screen is visible.
Yes, sir. Visible, sir.
Yeah. So in today's session, we will be looking at the physical platforms, basically hardware and software design perspective. Like Internet of Things, basically consisting of various physical devices of different varieties, and they will have different interoperability challenges. So we will looking at the physical design challenges, followed by we will be looking at the network design challenges, and then the logical design challenges. So basically starting with the first important aspect about Internet of Things. So let's discuss what is IoT basically. So when we talk about IoT, the full expansion of IoT is the Internet of Things. So within that, we can have different devices. Either you can have your home appliances, other important smart devices, smart watches. So things will be of different types. They were all having a different communication modules. They will have different operations. So diversified domain of things are there. And definitely whenever these diversified platforms are there, we will be having a different challenges that could be taken as a research opportunities to improvise something into the IoT. So I will be discussing also the different challenges within this IoT. So what is IoT is basically, it's a network of embedded sensors and actuators, and they all are now connected with internet to provide something smart applications. So whatever you say in today's scenario, a smart automobile, a smart transportation system, smart sewage system, smart water management system, wherever you see a smart word, basically it has a kind of devices that will be allowing you to make certain smartness. So when you will be thinking of these three important aspects, one is the embedded sensors, which will be basically bringing out the important data, crucial data. Based on that, you will be implementing some intelligent algorithms that could give you something crucial for management to decision makings to control. But the important problem in IoT is basically devices that we are using. It's not like equivalent capable like a computer devices that we have, like a desktop or laptops, will have an immense amount of processing capabilities. But when we talk about IoT, we will be having a very resource constrained devices. They were constrained with power, they were constrained with network speed, computing resources, and also there are other important aspects that will be also the part of constraint. So if you can look at this particular diagram, we have embedded sensors and actuators. They were operating in certain environment for certain smartness within that application. And basically, this is the part which comes under the physical design. So we will be having a physical platforms, IoT devices, sensors, actuators. So what are the important constraints and challenges are there in this particular design? We will be exploring. Thereafter, we will be moving towards the network because the communication is the crucial here in IoT, because we are integrating these sensors and actuators with internet connectivity. So whenever you have these many devices connected with internet, there are some network problems. There are certain network challenges. So we will be looking at into the network design, all such important aspects. And thereafter, we will be moving towards the logical design, where we will be having a cloud related stuff, semantic web technologies, and various communication APIs through which you can get the data from these devices and networks. Also, you can visualize these data, apply some analytics on the data, as well as you can control them from the remote location. So various kind of logics you can design over the logical design. So what are the technology roadmap that is important and crucial to make this IoT? So we need to understand the technology that derives the IoT. In physical design, we will be basically looking at the physical platforms. What are their resource constraint challenges that we need to address it, and how we can address them. So various kind of solutions as well as the problem we will be looking at the physical design perspective. In network design, we will be looking at the gateways, what kind of gateways we require to make these connections globally applicable, and what are the constraint networks, how we can organize the devices in a network, what are the self-organizing networks. So a lot of research opportunities are there in the network design, and we shall be looking at this important aspect as well. Logical design, as I already said, there are a lot many technologies that are revolving around us. Like nowadays, we are using a cloud virtualization technique. We are using a software-defined networks. We are using a fog computing platforms. So what are those platforms? How we can utilize them for optimizing a complete IoT network? Semantic web technology is basically an important technology that will integrate the informational network to your device. Basically, your World Wide Web data that is available on internet, how you can perceive that data, how you can understand that data. So kind of different semantic web technologies also very, very important to understand. So let's discuss important aspect at first. Physical design. What are the important challenges and what we need to take into our considerations. So basically, physical design will have various trade-off. Basically, when you look at a device, a physical device that you are planning to integrate in some smart applications, either your smart automation in some application, agriculture or automations, you basically have to look at the device perspective. So device will come with certain configurations. There will be having some CPU. There will be having some general purpose input output ports. We'll also have a certain performance constraints. So when we will be trying out to make a device which could improve the performance, then it will be degrading with certain parameters. Like size will not be the important attribute that will be degraded when the performance gets increased. Power when increases, then also there will be a cost that will be increasing. So there is a kind of design trade-off. Every time when you try to improve one, then there will be a degradation in another. So in order to simplify this particular problem, we have to decide what part we can keep it in the software side, what part we can keep it in the hardware side. So we basically need expertise in both hardware as well as the software. So you basically need a kind of different understanding from the sensor side also, and the kind of device that you are using, what type of sensors you are going to connect with that device. So imagine an application where you require certain sensors. You can look at it to the sensor perspective. Then what are the important parameters that you should consider while selecting those sensors? So some sensors are basically of analog type. Some sensors are having a digital outputs. Some sensor or actuators are derived through pulse width modulating signals. Some will have a connections like serial peripheral interface or I2C, UART or interrupt and timer. So these are the important categories that will be available with your physical platform. So if you have analog sensors only, then you have to look at what are the important ports are available on physical device where you can connect these analog sensors. Similar to that, what are the digital ports? What are the pulse width modulating ports? So there are different categories of input output ports, and that will basically help you to decide which particular physical platform is ideal for your particular application. So expertise in hardware is also very, very important in order to integrate some of the smartness in your applications. So hardware and software co-design becomes very, very important. In that, you should also look at the internal aspect about your physical device. Whether your device will have input-output interfaces of required quantity that you require. Processor, GPU, and CPU are the resources that you are going to use to process your data. And as we already know that IoT devices are constrained, they will have limited resources, and we have to process the data within these limited resources. So what are the constraints that is there with the processor, with the graphic cards, with the memories, and with the IO ports? So basically, when you look at the physical platform, you should expertise to get the finer details about the device. If you are interested to use Raspberry Pi, or if you are interested to use Beaglebone Black, Node MCU, various devices are there, or simple Texas Instruments, some microcontroller boards. You have to first look at the IO ports, whether the required amount of ports are available where you can connect your sensor. Sensor should connect to which particular port. That understanding is must. So in order to facilitate some of the IoT platforms for various smart applications, we have various options available in market. You can have Raspberry Pi board, Beaglebone Black board, MIPS Creator CI120. So these boards are basically used for your edge computing, basically for your edge of the network, where you have a sensors and actuator connected with this particular board. So you can choose these platforms. They will have a limited processing capabilities and storage capabilities. And it is not mandatory that you should use these platforms only. There are other microcontroller based platforms like Texas Instrument, TVC is there, and TMC4C is there. Various platforms are available. The important aspect for any IoT device is the connectivity, how you can connect the device with internet. So any microcontroller board you can choose for your smart application. The necessary thing that you should remember, the device should have some connectivity with internet. So it should not be like just a Bluetooth is a way of communication. Then you may find some difficulties. However, for that also in a physical design, a lot of different platforms are evolved. Like in communication side, you have 6 low-band devices. There you have Bluetooth and Zigbee, they can also communicate with internet. But the important aspect, you should decide which particular platform will have the internet connectivity options. So these are the few platforms I have used over a period, and I have understanding about these platforms. Beside that, I have also used microcontroller based platforms. I'll discuss about those. So what is the important thing that you should understand from these platforms? First, you should look at what are the sensors requirement you have in your particular smart applications. Then you should just go to these IO input ports. How many ports are available and how many sensors I have. So where should I connect these sensors? Because every sensor will have different peripheral interface. They may be connected with analog ports. They may be connected with digital ports. Then another important aspect for the physical design is the analog. If you have an analog sensor, because most sensors which we use will have an analog category. It's not like analog is only the one way, digital also available. But analog sensors are much more cheaper than the digital one. So when you have analog sensor, you should also look at the ADC in this particular physical platform. What is the analog to digital converter? The resolution. How much bit of ADC is available in these physical platforms. So with Beaglebone Black, you will have a 16-bit ADC, but with Raspberry Pi board, you don't have any ADC. You require a ADC board, external board to connect with Raspberry Pi board. So these are the important aspect you should understand before selecting those platforms. So here you can see you have only I2C UART communications SPI, but here you can get ATC also. That will give you 16-bit resolution. So you can understand how much accurate processing you can do it. If higher bit ADC is available with any platform, you should choose that one because it always give you the small variations. You can easily sense it with these kind of platforms. Beside that, in IoT domain nowadays we are using intelligent processing. We are performing various kind of analysis over data, and we cannot just restrict ourselves to just use that particular cloud computing platforms like Google, Amazon, and Microsoft is providing. These platforms are available over the public network, and when you send your data from your edge network, means basically you have deployed some devices and sending this data to process at the cloud server. And the cloud processing is basically taking a lot of time. Beside that, there is a kind of delay in a network which you cannot protect from your side. You cannot optimize it from your side because it is a public network. It is an internet where you cannot modify any device or any network through which you can optimize your data communications. So what is the best solutions? You can bring out the cloud near to your edge of the network where you have actual sensors and actuators connected with the edge devices. You should bring out the fog computing nodes near to that particular network. So your fog node is also operating in the same network as your edge devices are there. This will simplify some of the problems related to the latency and throughput, and you can optimize your computations and take immediate or real-time control and actions. So for that, you also have a separate set of devices like Google Coral board is there that will have the TensorFlow processing unit. So you can perform various kind of machine learning related processing on this particular board. So you can consider these board as a fog node in your design. Similarly, you also have a Beaglebone AI boards. These board also having a lot of processing capabilities, and it can process your data very fast. So you can use these boards as also a fog node. However, they are not very powerful, similar like GPU systems are there for scalable computations. However, you can create a network of these devices and create a distributed computing platforms. Similar to that, you also have a Jetson board option. You can also choose this particular board because some board will have limited external GPIO ports. If you are not connecting any external sensors on these particular boards, only the processing is the important operation, then you can choose these boards. They are also available in a market, and they are not also very costly. So this is all about the devices that is there in the physical design, but they are also imposing some challenges, and those challenges comes under the edge computing paradigm. So edge computing is basically what? Your edge devices in a network, basically receiving some sensors data, and then they have to process this data to take intelligent processing. What is the current problem? With the current cloud system, if we do all processing at cloud and get back the control to the device, will take a round trip time. and in between that, the public network may have certain congestion problems sometimes, may have certain network disconnection interruptions that will affect your control decision to propagate at the edge of the network. So what is the good solutions? You can process your data at the edge device itself. And nowadays, if you can look at various edge devices are available, either you can use directly these Google Coral or Beaglebone AI boards as your edge devices and process your data on these devices rather than sending it at the cloud server. Okay, so various solutions are available which you can use it to solve some of the physical design challenges. So what are these challenges? Let's look at into this. First is the constraint data processing methods. You should implement some of the algorithms, some of the methods that could take the census data and process it over the edge devices itself. Nowadays, you are seeing the smart watches. They were having a self-processing unit inside the watch that will take your BP and temperature and other details, like how much walk you have done, how much time you have running you have done. So all such analytics, it will be collecting and deriving some of the predictions out of it. So kind of edge computing paradigm is now shifting towards the one integrated device could do all processing as well as the analysis on the data. So right now, if you can look at, we have a certain challenges in constraint data processing. We basically required some conversion mechanism because the sensors are of different types. Temperature sensor generates some temperature type of values. Some sensors generate analog type of values. Some sensors will generate ASCII kind of or bit format type of data. So when you have a different type of census data, you require an optimized method that could convert this particular data in one unified format. Similarly, you should also validate that the data generated by the sensor is correct or not. Then you also require some sorting to process the data, and then aggregations, what way you can unify the data in one particular format. So you can perform various analysis on the data. Like we use a CSV file for various machine learning models. Kind of aggregation. When you have data coming from the all sources, you should aggregate them in one single format. That can be processable. Then analysis, you should also do it on the edge devices. So you implement some of the algorithm that will take less amount of resource to process your data and generates the report. That report will contain the important aspects about the analysis of the result. And presentations is also very, very important, how you can visualize your data. So you have various forms, histogram, you have a line plot, you have various type of plotting and presentation mechanisms. So these are the challenges in a physical design. When you design an IoT device for certain smart applications, and every processing that you wanted to do at edge node, you have to deal with these processing constraints. Unique identity. So this is what the term we will cover in the network design. What is the unique identity? Dynamic and self-adaptability is also a very, very important challenge. Basically, it comes under the network also in a physical design also. In network, we will be having a self-organizing network where we implement some algorithm that will adapt the changing context. As the context is changed, that device will also do optimizations and dynamically adapt the behaviors. In a physical design, how it can be beneficial? So in physical design, like energy you utilize for communication. If your physical IoT device will have a Wi-Fi module or a Bluetooth module, various other communication options. So what way it can be optimized? So you can operate a device in if a particular IoT device operated with battery, you can start switching the mode of the devices. For communication, you can do for a fraction period of time and then keep the communication module in a sleep mode. So kind of way you can dynamically adjust the requirement for energy. Bandwidth, similarly, your basically internet communications will have a busty networks, busty communication, busty traffic. Your data is sometime will be 1 Mbps, sometime very low. So you will not be able to adjust the bandwidth always uniform. So whenever you will be having a limited bandwidth, you should start creating the packets of smaller size. So traffic shaping algorithm you can implement on edge devices so that you can deliver your data with a limited bandwidth. Medium access, you should also see in some of the devices will have a kind of shareable channels. So you have to share multi-channels for communications. This is an important aspect. We will be looking at the network design in more detail. Self-configuring, so your device should also have some capability, some smartness. So whenever there is a certain device in a network, so it can immediately sense that device and try to allow that device to get connected with the network. So kind of self-configurability is also a part of network. We will be looking at these aspects in the networking domain. But how it can be used in physical design? So self-configurability, you can bring it into the device whenever you are observing some sensor data is not correct and there is a deviation that is under the threshold limit. So you are saying that device is working properly but required a reconfiguration. So your physical device or your edge node will automatically recalibrate the sensor's value so that it will start getting it in the correct order. So kind of self-configurability device can also get from the physical design perspective. Interoperability, it basically comes from the all aspect, either you talk about physical design, logical design, or your network design. Interoperability is basically the device will have different standard. They operating with different communication modules and they have a different operating environment and conditions. So when you have diversified device platform, you require to integrate them into the informational network and you require one unified format of communications. So whenever a new device introduced in a network, your particular gateway or your particular edge device will recognize that device and allow that device to get integrate and do communications. So interoperability is the biggest challenge at present in IoT domain. And there are a lot of work is going in this particular domain to create a kind of cross layer that will allow other devices to be integrated very easily. Integration to informational networks. So nowadays, if you can see devices required to connect with internet and perceive the informations that is available on internet, like World Wide Web. Lot of data centers are there, lot of news agencies are there, their data servers are running. Similarly, geostationary satellite data is coming on the certain weather stations. So lot of data is available already. We have to identify the mechanism through which we can easily communicate with those existing informations. So in World Wide Web, we have RSS feed. So some news data can be taken from that particular server and it can optimize the intelligence. So you have seen recently Google has introduced a kind of Google Assistance. That Google Assistant will book your appointment. It will identify the physician calendar and look at what are the free slots are available. So it will identify those particular informations from his calendar and fixing the appointment for you. Kind of different semantic web technologies are available, like Alexa, Google Assistant for playing music and other important resources that is available on internet, can we utilize it for generating some intelligent devices? Fault tolerant. So device should be fault tolerant. If it can detect any kind of fault in an IoT device, it can immediately respond by certain alert, or it can do self-isolation. So that will brings the kind of smartness. If any attack happened, then device should respond immediately. So it can protect that particular attack to propagate in the whole network. So it can self-isolate, it can reconfigure, it can reset. Various other ways you can protect the physical network from being attacked or from being any anomalies that could create a lot of quality of service issues. So edge computing paradigm, as we are discussing, we basically at the edge of the network where we will be having a IoT devices deployed for certain smart applications. So they can just get the sensors data at the edge of the device, and there itself they can process it and take intelligent decisions, rather than they should go to the cloud server for processing and then take an important decisions back to that device. So edge computing comes into the lower portion of the network where you have actual deployment. Fog computing basically comes at the gateway side where you will be having a cloud similar, smaller platform where you can process your data and take important decisions. They are time dependent. So like real time, you have to take certain decisions. There you can use the fog node, an alternative of cloud computing. Then cloud is obviously available for scalable computations. So what is the advantages and what is the benefit of edge computing? As I already discussed a lot, low latencies, energy is required less, time is required less, because the round trip time is not dominating in this, because your device is also located in the same locations. So latency is negligible. Connection reliability will also not be interrupted in the edge computing, because you are not now depending on the public network, you are depending on the private network. So your network will have edge devices, fog devices. There itself you are revolving your communications data and analysis. Data management is also not a bigger problem, because when you are using a cloud server for storing this data, then you have to depend on the cloud and the connectivity with the cloud. But if you are storing your data for a smaller applications, I'm not talking about the big data kind of analytics where we required thousands of sensors data coming and you have to process that data at fastest rate. So in that case, there are the cloud systems that can only help. But I'm talking about the domain specific smart applications like a home automations or device control from the home locations. So very domain specific applications will have a data that can be easily stored in the fog devices rather than looking at the cloud server. Security and privacy will also improve, because now the public network entrance is not there. If public network exposure is there for the network, then there are many more attacks can happen on your particular private network. So it is very, very secure, and privacy will also be maintained properly. And lightweight analytics you can perform in the edge computing paradigm. You need not to look at the cloud server for processing. So I'll discuss about these applications. Some of the work we have already done in this particular domain. So in the next session, I'll be showing you some of the work which we have done it with the actual hardwares and softwares. So constraint data processing, I already discussed what are the important challenges that we need to address in order to make the IoT device self-alone for processing to analytics to take important decisions rather than looking at the other cloud integrations. So conversion is the biggest problem, because sensors data are coming from different devices and different formats. You require a conversion. into one uniform format that can be processed by your analytics at the edge of the device. Validations, you should ensure that device data that you are getting is correct or it's clean from any kind of anomalies. Shorting is a kind of arrangement that you can do it for analysis of data, like maximum value, minimum value. In that threshold limit, you can perform certain event-based processing or event-based analytics. So sometimes we are not looking at the all data. We are only important when it is crossing the threshold limit, when it is generating that event. So in that case, the shorting can be very much useful. Aggregation, as I already said, combining data. So right now we are using aggregation base 64 encoding, through which we encode the entire data in base 64 format. That basically helping us to transfer this data to the cloud server or fog node for processing. Analysis, you can do a small lightweight algorithm, decision tree based algorithm, some machine learning algorithm. You can implement on the fog node that I have shown you, like Google Coral or Beaglebone AI boards. Reporting you can generate and presentations you can generate out of that data. Fault tolerant, as I already said, physical device needs to be fault tolerant. The data that you are getting from the sensor, whether it has any anomalies, any kind of wrong data, false data, you should find out the mechanism to protect such problems for making the important decisions. So data is basically a fuel for your analytics. And if this particular data will have certain anomalies, then your prediction will not be accurate. So to protect those predictions, wrong predictions, you should apply some mechanisms. So basically fault that will generated from the sensors are of two types, like behavioral fault and persistent fault. And how you can diagnose a device will have, a sensor will have the software fault or hardware fault. Related to that, we have used a probabilistic neural network. I will be discussing in next session how we have implemented to detect the sensor has a fault or not. Similarly, persistent fault will have permanent, intermediate, and transient fault. They are basically time variant according to the time they will be operating. So permanent fault is all the time device will not operate. Intermediate fault for a small time interval, let's say for 10 seconds, the data is not correct. And rest of the time, it is giving the correct data. Transient fault is very difficult to identify because they generate what for very short period of time. Just 1 second, the data is incorrect, another second data is correct. So kind of these are the faults that will come out of the sensors. And to diagnose that, we have a mechanism. Optimizations, how you can optimize your computations. Basically, what I have talked about in edge computing, there are certain challenges in terms of processing your data and taking control out of those devices at the edge of the network. There are some solutions through which you can optimize your network. You can go with a container-based virtualization. It is another kind of virtualizations. It is totally different from the hypervisor-based enable virtualization. So here, basically, what advantage you will get? Basically, the class or container-based virtualization is a microservice that you can operate with a limited processing capabilities on any device. Rather than hypervisor is basically splitting your hardware based on the available resources. If I have one core processor, I have a certain amount of RAM spaces. So it will split it and create a multiple VMs. But all the VMs running in parallel is a kind of difficult for a system which has limited resource. So for IoT devices will not have amount of resource that can create this kind of virtualization. So we will be having container-based virtualization. Here we will be getting a kind of benefit that we can create multiple containers within a small amount of resources. So it is much fastest, and you can run parallel and independent models. So one model you can run for processing your data, one model you can run for analysis of your data, one model you can use for presentation and reporting of data. So this is what very feasible in your IoT devices rather than the hypervisor based virtualization. So how you can enable the container based virtualization? There is a Docker. So Docker is a way through which you can create virtualization, that is container based. Other optimization how you can do, so data aggregation, you can use base64 encoding scheme to unify the all data coming from the all sensors and make it one uniform format that can be transferred to the other networks like fog networks where you can process this data. Low latency and throughput, for that you can implement some data compression techniques. Some algorithm you can design that can process the data and find out what are the data which can be compressed into a small format. Dynamic and self-adaptability like traffic shaping algorithms, I'll discuss in the network side. Data validation and completeness, so how you can say that data is complete and correct. For that, we will be having a small algorithm, a probabilistic neural network. I will be discuss that in the next session, where we can sense this data and identify what are the faults are there in this data. Outlier detections you can also implement on the edge devices. You can detect whether the census data generated are within the limit or it is crossing that limit, or data is not at all the part of the cluster that we have generated from the past historical data. So outlier, local outlier factor is the algorithm that you can implement in edge devices to identify data is outlier or not. Similarly, you can apply data imputation technique where you can find out if some data is missing and that is not coming from the sensor. So you can use the historical census data to predict based on the other census data, what is this particular missing sensor data. So you can have KD tree, K decision trees through which you can also identify that. Machine learning models you can implement like probabilistic neural network for fault diagnosis, and informational network interoperabilities. So you can also have a technologies like Semantic Web Technologies where you can transform your web data into a kind of data that machine can understand. So for that you have RDF, OWL. These are the ontologies technique to which you can connect the data or different attributes or entities and create a kind of meaningful output. And to process this data, you can have a Spark query, like SQL we use for relational databases to extract the data. Similarly, for these ontologies which you create or these vocabularies which you create with the OWL can be processed with a Spark query algorithm, basically the query language. Unique identity, your device should have some network card or NIC card, network interface card, through which it can be connected with internet. Either your device should have a Wi-Fi or either Ethernet connectivity. Other devices that you can connect for internet connectivity is 6LoWPAN. So you have a Zigbees, you have a Bluetooth, you have various other devices. They are also supporting IP. So if your physical platform will have those particular 6LoWPAN devices, you can still able to connect it with internet. But not like the device following the IEEE standard 802.15.4 like Zigbees and other devices. They are non-IP based devices, NFC card, or you can say your Bluetooth, normal Bluetooth, not the BLE standard. So there you will be facing difficulty to connect the device. So you should identify from your physical platform what are the available communication options are available. Lightweight database is also available that you can run on the edge devices like Berkeley DB. They are very, very small, like a 1 MB of library they have. That will facilitate all the schemas and the data storage tables. So kind of various level DB is there, object box, real MS, Redis is a memory based databases, RocksDB. So these databases are very lightweight that you can use it with the edge devices, and that one device can do all computations, storage and processing. So various platforms are available that you can use it for this. Physical platform for network design. So network design is also very, very important to understand, because it is going to give us the kind of connectivity between the devices. So it is not like just one device we are using for a smart application. When we talk about the smart cities, so within that smart cities, you have multiple different problems that you are addressing with the IoT. So smart water management to smart air pollution monitorings to smart transportations. So various smart applications are there where you are not just working with one device, you are deploying a network of devices. So when you have a network of devices, definitely there are certain challenges that needs to be addressed properly. So if you can look at the predictions that was made in 2020, we will be having a 50 billion devices connected with internet for some smart applications, to 1 trillion by 2025. These are the predictions gave by various industrial tech giant companies. So they are expecting that there is a biggest potential in IoT, and coming days the IoT is going to be everywhere for certain smartness. So you can imagine when you have a billions and millions or trillions of devices connected with internet, what are the potential problems that can be important to solve. So basically, your IoT network will require a kind of connections that could remain active for all time without being affected from any kind of interruptions. So IoT traffic differs significantly when these billions of devices connected in a network. You can understand that traffic that they generate definitely choke the entire network or public networks. So we required some optimized method to make the IoT communications more proper. So within that, various platforms are available. Nowadays, even cellular network side, we have various options through which also you can communicate your IoT data. So what are the challenges? Let's look at into this. So latency and throughput is definitely a major one, because currently we are operating with IPv version 4, and which has a limited communication capabilities, limited number of IP addresses we can get it through it. So we required a kind of mechanisms to optimize our network latencies and throughput. So what kind of architectures that we should adapt, what way we can optimize it. So we will be discussing about that also. Fault tolerant and scalability. So it should not be like one network you have designed for smart application and that remains for all time. It is not like that. In the future requirements, we will be needing some more 20 or 30,000 devices to be integrated. So when you have a network, it should also have an options to scale it. It should not be like just limited to specific configurations. So kind of requirement from the fault tolerant and scalability side. Dynamic and self-adaptability, as I discussed, device should have the capability to change the inner concepts, like when the bandwidth is high, then you should send a bigger chunk of data. When bandwidth is low, you can reduce your data communication. When batteries are low, then you optimize the communications using a sleep and wake mode of device. So kind of different dynamic and self-adaptability your device is needed in a network. Interoperability is definitely a biggest challenge because we are not just dealing from the one design perspective. In a physical design, we have different devices and we need to integrate them in a network. This is a one challenge. Communication side, you have different type of communications, Bluetooth, Zigbee, near field communication, and from the large communications, you have a cellular communication. So device can come with any communication and you have to integrate them in a network. So once you have a smart application where you have a kind of data generated by one communication module, and once you bring out another LoRa communication, let's say, presently your network is operating with Zigbee. When LoRa communication device you bring into the network, then your network is not responding it. Then it is not a kind of network that will be scalable, that will be interoperable. So it's very, very important that every device should get connected with the internet. Integrated to informational network, so your device should talk with the World Wide Web data servers that is located throughout the world for different applications, and from there they can get the data to give some intelligent decisions. So you have heard about various integrations haven't happened in last few decades. You have seen Amazon Alexa is there, Google Assistant is there, like Watson computer is there. They all are connected with internet and they are getting the intelligence from the available data. So device should have kind of mechanism to connect with internet and get the data what is required for taking any predictions or intelligence. Self-configurability is very, very important. Device should configure whenever there is a fault, whenever there is a kind of attack on a system. Information security is very, very important area in IoT domain because we require a lightweight encryption techniques, lightweight authentication techniques that will keep your system remain available for all time. Unique identity and gateway capabilities. So here we will be discussing about non-IP and IP-based communication devices. So what are the platforms that are available for a network communications? So we have a fixed and short range devices. If you have a network perimeter not more than a kilometer, then you can go with these devices. If your network of communication is beyond territory, like subcontinent or between the states, you can go with the long range technologies. So these two different platform categories are there which you can use for your smart applications. Bluetooth, BLE devices, Zigbee, Thread, Z-Wave, wireless HART, 6LoWPAN, near field communication and radio frequency identification, infrared and Wi-Fi. These are the short range communication devices and they basically work on the radio frequency, simple radio frequencies. Long range technologies, they are basically works on modulation techniques and they are basically operated in a cellular network like our mobile data communication. It's a cellular network. So these devices, some of the devices are operating with cellular network, some of them are operating with the normal RF like a LoRa. So I'll be discussing about these devices. So personal area network devices, in that we have seen like some devices they are operated with IP, some devices they are operated with non-IP. So device which is non-IP based devices are very difficult to integrate with the public network. Like Zigbee, you cannot directly connect with internet because it doesn't support any kind of IP, the logical address that identify a device in a network. So they are following a standard of IEEE 802.15.4. So within that, they have a different mechanism to identify a device that is a kind of 16-bit address. Bluetooth, Z-Wave, and wireless HART, these are the non-IP based devices. So in order to connect these standard devices, we required some gateway. The gateway should have kind of communicating devices that can translate this data into the IP network compatible format. So when you have a devices and you're interested to connect them, you require a gateway solutions to solve the problem of non-IP based device connectivity with internet. But you have also have personal area network devices. They supports IP. So 6 low-band devices are there. Like you have a Zigbee near neighboring area network devices. So here you have a Zigbee that can also communicate with internet and having IP support. Thread is a kind of device which basically work with a non-IP based standard protocol defined by IEEE 802.15.4, but they also provides you the IP. So the information that generate from these devices is getting translated into the IP domain. That is why they are 6 low-band IPs. So personal area network devices with IPv version 6 support. Similarly, ISA is there, industrial standard automation. This is also a protocol used mostly in industrial automation. So you can look at these devices physically, how they look, and they are also available. If you are interested to use them, you can have an opportunity to use them. And if you can look at how to integrate these devices, you have a various interfaces like SPI interface. These devices are support. Otherwise, they support I2C or UART communications. So you have various communication interface. So you can look at the physical devices, whether your device will have those interfaces or not. So that will also give you a kind of understanding. So what is the important parameters that you should understand from these communication devices? So first is basically the frequency band, at what frequency band they operates. Then thereafter you have to look at their data rate, at what rate they can transfer your data. So signal rate, this is also very important. And then the range, at what range they can communicate, so that you can deploy your network according to that their range. Another important aspect is the power of transmission. So if the power of transmission is lower, then your communication is not too very far. If the communication power is very high, then you can communicate to very far distances. So number of RF channel, this is also very important, and this is what the most important one, because that will allow you how many devices can operate in a coordination of one device. So if Bluetooth you have make as a coordinator device in a network, then 78 other devices can operate within that particular coordinator. So kind of the channel, how many channel a device can support. If you have more number of channel, you can effectively communicate in a network, because when you share a single channel, then you require a algorithm to manage those communication, and there is a high chance that collision can happen. So if you have independent channels, you can communicate very effectively. Like we use Wi-Fi routers in our home, and we can connect multiple devices with Wi-Fi router because it supports multi-channels. Each channel will be given to one particular device, and it can be very effectively communicate. So these are the important aspects related to the Wi-Fi or different standard of devices. When you interested to use any of these communication device, please have a look on these important specifications. That gives you the kind of understanding how I can do my network deployment, what communication range it can support, and what are the number of channels through which I can communicate without being sharing the channel. So in Wi-Fi standard also you have seen different standards. Nowadays the Wi-Fi routers are coming with 5 gigahertz band also. So 5 gigahertz band definitely gives you the higher throughput. So maximum data rate 54 Mbps you will get it. But the distance of communication will reduce, because you have the concept of this communications. When you have higher frequencies, then you have a data rate higher, but the distance will be lower. But when you have a frequencies lower, then range of communication is higher, but data rate will be smaller. So according to that standard, you have various devices. You can optimize your network by using a suitable type of device. If you are interested to operate your network with 5G, 5 gigahertz band, then you can go with it. and 5 gigahertz band will give you the more number of channel as compared to 2.4 gigahertz channel. So I'll be discussing about why I'm talking more about the channels, why they are very important. Long range technologies, they are basically available like LoRa. LoRa is a kind of communication operated very low frequency. That is why they can communicate up to 15 or 13 kilometers according to that standard. And they are not using any kind of cellular communication. It is free to use this particular frequency. So it's a unlicensed frequency, and you can operate these type of communication without being violating any frequency licensing issues. You also have a 4G LTE. So LTE-M is basically a 4G modem. Nowadays they are also available. If you are having any communications that you wanted to pursue through cellular network, you can go with 4G modems. NB-IoT is also available, is another kind of communications, mostly adapted by Vodafone, Jio, and many other companies. This is also a kind of communication operate through cellular networks. And RPMA is also a cellular network communication hardware that you can use it. Only that from all hardware, Sigfox is only the software solution provided to the devices. So you can download from the Sigfox website a package. Similarly, RPMA package is available that you can download from their website and install in your Raspberry Pi board or a Beaglebone board to get the kind of communication that Sigfox provided. So it is basically a French company who introduced this protocol where you have a limited communication. So certain restrictions they have imposed in these protocols. So you can go through these devices. They can also be useful for integrating into your device network. 5G is still not yet available. Once the 5G will come, we will be not having any problem with the latencies and throughput because it is very, very fast operated. And it also supports the infinite bandwidth. Oh, sorry, infinite number of channels. So you need not to worry about that. I have 40 channels. I can only communicate with 40 individual channels. But 5G will provide you the infinite channels. You can connect any device network. You will not face any kind of issues related to the latencies and throughput. So how you can optimize your device network? There is a research domain within that many researchers are working. This is called self-organizing network. It is basically an automation technology designed to facilitate planning, configurations, management, optimizations, and simpler and faster way of operating your network. So basically nowadays, whenever you create any device network, device should do automatically many things like self-healing, self-configuration, self-optimization. And these are the intelligence we have to incorporate in our IoT networks. Then only we can say our device is a dynamic and self-configurable, self-adaptable, and it can also do self-healing, so fault tolerant. So these are the important areas where you can target your research. I'll discuss each of these attributes. What are the key components of self-organizing network in IoT? Basically, one is the neighboring discovery. So you can discover what are the resources available from the neighboring devices. Like I have discussed about the integrated to informational network, semantic web technologies. So you have available resources, you have to discover it, what resource is useful for you. So in a device network, when you have multiple devices, one is looking at the temperature, one is looking at the fire accidents, one is looking at the other kind of sensing. So in order to take important decisions, you require the resource, you require the discovery of the particular census data. So some device operating temperature, then temperature data you get it from one device. Similarly, you can get one device data humidity or precipitation, and you can take an important decision that today rainfall possibility is what. So this is what neighboring discovery is a one more important attribute. Besides that, for new device, when you introduce in a network, it is also very, very important to connect that device in a network. Media access control. So as I already discussed, when you have a device which operate with a certain standard, will have a certain number of channels, and you wanted to optimize the channel utilization without affecting any collision in the network. So you can introduce some media access control protocols, or either you can use a device which has multi-channel support. Local connectivity and path establishment. So whenever any new device come in a network, you should establish the connection with the device. If one particular gateway is not working, then your device will make a switch to another gateway. This is what the way to adjust the fault in a network. And you can also establish the path that could be optimize your network communications. Service recovery management. So service recovery management is like when your device basically getting faulty, and you should get notified for these particular kind of fault in a network, and through which you can take important decisions. So your device will do self-isolation from the network. So it will no more part for any routing. It can just avoid the communications. And still your network should survive. It should not like just one device will getting affected and your network is died. Energy management is also very, very important, because you wanted to save the energy requirements for a resource. So some device may be operated with batteries, some devices may be operated with limited computational resources. You can optimize that also. So these are the few open research domain where you can target the optimizations. So the critical properties that is very, very important for self-organization IoT is a cooperative communication model. Cooperative communication model is what? As I said, Zigbee, Bluetooth, other different device standards are there. They should all come together and create a kind of cooperative communication model. So you require a kind of cross-layer design for self-organization. So whenever a Bluetooth or a LoRa device come together, they should have some mechanism in between that can help to facilitate the communication between the device network. Another is a situational awareness. So device network should not be like a passive network. Once you deployed it, it is operating as what you have done it for the requirement. So it is not modifying itself. It is not making any changes into the system. So if some device is faulty, still your network is running that device in a network. It should not be like faulty device should be isolated or reconfigure it. Similarly, if one topology is not performing well, then you should switch the topologies between the devices. So these are the way to which you can make the device network standard. Automated load balancing. So as I said, this expansion and scalability is the need for smart applications, a need for smart cities that we are now planning. And within that, if 100 device we have connected with one gateway, and 100 device will have a bandwidth that is split among the all 100 device. Let's say 100 Mbps is the bandwidth, and 100 device we have connected between with one gateway. So each device will get 1 Mbps of standard bandwidth. Now we have connected 100 more devices. Now your bandwidth is furthermore split. So it will be 0.5 Mbps for 200 devices. So it should not be like when you increasing the load, it is going to affect the quality of service. So load balancing should be in such a way that your quality of service should not get hampered. So what are the research open problems? You have to implement some cross-layer design for self-organization. So if any device will come from any standard, either Zigbee device, LoRa device, NFC, RFID, any device will come, there should not be any kind of problem that we have to manually feed the code and do the modification in the code that will allow that device in the network. It should be self-organizing. Whenever new device will come, it will automatically allow the device to do communications. Obviously, there is a requirement for security because we want to make our network more and more secure, and authentication is also a kind of we required to save our network. Heterogeneity in self-organization is also very, very important. As I said, heterogeneous devices are there. Homogeneous network is not there in IoT. It is a heterogeneous network. So whenever heterogeneous device comes together, they should have some mechanism to self-organize. Multi-radio, multi-channel communications, as I said, you have a limited number of communication channels and you have to optimize it. I have given the example for the scalability. When you have one gateway which is providing each device 1 Mbps of bandwidth, and when you have attached 200 more devices, you should optimize your channel utilization, because your Wi-Fi router or your gateway will have only limited number of channels, and when you added 200 more devices, means 100 more devices, 200 total devices, then how you can manage your channel communications. Low power computation and load balancing. This is also very crucial for battery operated devices or the device which has limited resources. Delay tolerant network over self-organizing networks. So your network should not be having more and more latencies. It should not be just entered into the loop. The kind of network which could detect the requirement for quality of service. It should not be like the latencies keep on increasing when more and more devices is getting connected with the network. So challenges, what are the challenges are there? So a self-adaptive cross-layer model for self-organization in IoT, which is aware of scale, energy, communication resource constraint. So you have to take into account what are the available resources your device will have and how you can optimize them. So what are the challenges they are open? So according to those particular resource requirements and constraint, you have to optimize your device network or device communications. Another challenge is network intelligence to drive barrier between type of service supported in self-organizing network of the IoT. So as I said, when you have a different device, LoRa or Zigbee or NFC or Z-Wave, they should not just intervene any issues in a network. They should also be allowed to connect in a network, and they can also pass their data. So some kind of cross layer is required and facilitate that kind of communications. Reliable and automation detection of self-organizing network and prediction model to storage need to support DTN over the self-organizing network. So there are some more intelligence that you require. You can devise your device itself to operate as an intelligent prediction model device, or it can also take some important decisions when to store the data, what data should be stored, what data should not be stored. So self-organizing network is required. Multi-radio channel communication. So here what we are doing, basically we will be trying to utilize the channels in more effective way. Like you have heard about multi-hop communications. So how you can facilitate multi-hop communications? You can use a different channel for communications, and then you can transfer your data. Or you can have a similar channels that you can also use for communications. So here you have to utilize the channels. How effectively you can utilize the channels that can transfer the data without waiting for getting acquired that channel. Like in IEEE 802.15.4 standard, we have a CSMA CD, carrier sense multiple access with collision detection protocol. So this particular protocol facilitates the channel sharing mechanism. So we have to optimize it so that the channel should be shared equally among all the devices in a network, and it will not affect the quality of service. Low power and load balancing, as I said, for that you required a lot more understanding towards the kind of requirement you have in your system. Like you have a lot more communication that should be frequent. Then how you can optimize your resource, how you can optimize the low computations. So for that you have a kind of different mechanism through which you can analyze what are the important factors that could affect the computations and overutilization of power, and they can also affect the load into the system. So you can have idle listening, overhearing, collisions, protocol overhead, neighboring monitoring and securities, routing, topology, and packet loss. So these are the mechanisms through which you can look at what are the resource expensive application or a program running inside the IoT device. And that could be optimized to minimize the computational requirement. And that could also be equally distribute the load among the other devices. Unique identity, as I discussed, that the device should have some IP to configure into the network. Then we will say that device is a IoT device. But when device will not have that communication option that could give the unique identity in the network, then we should have some gateway that could facilitate the communication of the non-IP based devices in an IP network. And there are many gateways are required to facilitate in such kind of network. So this is what the essential requirement for the device if they are from multiple communication modules. So interoperability is kind of solution we can propose it with the help of gateway, so that every device with different communication can be integrated with the network. Interoperability, so this is what a kind of problem. It is not just comes to the physical design or network design, it comes to all different designs. So device side, you look at different capabilities devices are there, different communication protocol are there. You require to integrate all of them in a network. So you require some gateways that could help to integrate those devices easily in the network. Synthetic side, you can also see data format, schema, interfaces. So you require some unified format to process the data. So synthetic side also you have to look, because some device will programmed with Python programming, C programming, Java programming, will have different formats, different data structures to store and process the data. So you require mechanism to introduce some cross layer that can facilitate these communications. Like we nowadays see a cross compilations. So Python code can be compiled in Java, and different cross compilers are there. Similarly, semantic side, the data model information and ontologies, these are also a kind of problem that we require to handle it, so that device when connect with a network can also connect the street side cameras to perceive the information from there to take intelligent decisions, and various other interconnection between the devices, or the data centers and servers that they are already available in World Wide Web domain. They can also provide informations for smarter decision making. Platforms, operating systems also different, or data structure also different, programming language is also different. Besides that, networking side, we also have wireless and wired. So a lot more opportunities open for everyone to do a research on these interoperability challenges. If we can able to make a self-organizing network which can modify according to the context, according to the different interoperability requirements, then your network is kind of complete network. Information security is also a major issue at present in IoT network, because we require to implement some lightweight encryption techniques, lightweight mechanisms to communicate between a devices or between a networks. So we require to ensure the confidentiality, and different mechanisms are there. Like encryption is one of the most widely used one, but we require lightweight encryption that can be run on the device. And it is not like that encryption that we have implemented on device. It is doing that encryption only and affecting the quality of service. That is why we require kind of encryption that will not affect the quality of service. VPN and tunneling options are available. That is kind of a secure tunnel through which you can communicate in a public network. Access control links, like you can create some intrusion detection systems, firewall systems. They are light in weight and they can safeguard your confidentiality. Similarly, authentication and integrity management is also important. So you can create related to your data, what are the integrity issues are there, whether data is going to get changed, or what is the source from where the data is basically originate. So every authenticity is also very, very important. Authentication side, you can have also various options, public, private, key-based authentications, biometric based, and different third-party certificate authorities are there that will also allow you to authenticate on a system. So authorization, intrusion detection, and preventions also very, very important in IoT network, and they are also open as a research domain where you can implement such a system which is safer from the malicious attacks. Trust availabilities, apply penetration testing. So you should, once create your network, you should test the quality of services, whether your network is providing the quality of service or not, or it is keep on doing the encryption rather than sending the data. So kind of various analysis you require to do once you have the information security in your system. Also, you should apply some penetration testing on your network, whether the network is vulnerable or network is properly saved. Another important device in a network is in IoT domain is a gateway. So gateway, you should choose the gateway which can support a multi-communication modules or multi-communication protocols. So internet side, you can have a 3G, 4G communication from cellular network side, Wi-Fi, Ethernet from the normal internet connections that you have it, and it should also support IPv and IPv4 and 6 versions. Beside that, it can also have enough processing capability to process your data, lightweight processing, reasoning, you can do it. Some encryptions and firewall you can implement on these devices. And from the lower end, you should also have a kind of devices that can support the personal area network communications, like 6LoWPAN, Zigbee, Bluetooth, NFC. So multi communication protocol support is required at the gateway. So your smart gateway should be like that. It should have local database operating system, and it is kind of a single board computer or AI computer that you can use it in place of gateways, or you can use the gateways like routers at your home. That can also help you to make a secure gateway connections. The last one design is called a logical design, where we basically look at the APIs. What are the different APIs we should use? What are the backend requirements we have? What is the edge requirement we have? And what is the integration informational network requirements we have? So when you have decided that this is what my smart application will do, it will communicate with the World Wide Web servers where the data is available. It will also get the data from the edge network devices. It will also save the data in historical databases from where I can also fetch the data and do certain analysis. So different purpose, different API support we have. So behavioral requirements will also be very, very important in logical design framework, like manual or automatic. What are the system operation that you want to keep manual? What are the system operation you wanted to keep it automatic? So still we are not entered in an era where we can give all the critical controls to the IoT intelligence. Still AI is not up to that mark that can take the important decisions and operate the device. So The important and critical controls, you should make it manual, and the rest other controls that will not hamper the quality and hamper the destruction. So normal operations. So you can consider those parameters into your considerations and design your logical design framework. So backend requirement is what, like access of historical sensor data and context analytics and edge discoveries. So these are the requirements from the API side. Edge requirements, when you want to connect the device, what discovery you want to apply on a device, device access, real-time data you required, or real-time actuation you want, kind of different requirement that is there with the APIs. So according to that, there are communication APIs. They are very responsible for making these communications between a device, between the web servers, and between the cloud servers. So the most popular one is a representational state transfer architecture. This is a REST API. Within that, you have functions like get, put, post. And this particular protocol is also having a lighter version of it, Constraint AP. This is a protocol that you can use for device discovery or resource discovery in a network. It uses this particular representational state transfer protocol, but it is operated as a UDP protocol. It is not a TCP protocol. That is why you can use in a private network this protocol rather than in a public network. One more important aspect with the REST API is that it provides you the URI. URI is very, very important. It's a resource, a uniform resource identifier. With this, you can distinguish the resources. What are the resources you have in your system? You can distinguish them. This is very, very important in your semantic web technologies. In semantic web, you have ontologies, you have each particular type of attributes that you wanted to access from the web. Then these URIs is going to help you to get those particular kind of data. So it also supports different type of data exchange, JSON format, binary format, and other representations like CSV data, a different type of data format it supports. And the main function that it uses, get, put, post, delete. Each function will have different functionalities. Get will list out all the data. Put basically do a kind of manipulation into the data. Delete will delete the data. Post will post some data into the system. Beside that, you have other protocols specifically designed for IoT like MQTT. HTTP is used in a normal web communications. It is also used in IoT applications. But the lighter version of it is MQTT. It is based on a publisher-subscriber model and very effective protocol that you can use for device communications. And various cloud platforms are available that provides you MQTT communications, like Amazon, Cloud MQTT, various other are there. DDS is a data distribution service protocol that you can use for only data communications. So very, very data-centric communication protocol. It also supports publisher-subscriber model for communication. Constraint AP basically use the REST API and it is used for lighter weight communications. XMPP we are using in our WhatsApp messengers. This is a protocol that will provide you the real-time information about the system. Whether system is status of the system, you can monitor it with this particular protocol. Very effective. Integrated to informational network, as I discussed, what you can do, you should learn about the semantic web technologies, what they can do. It can create a kind of virtual entities. It can connect the information that available in the public domain, web servers, and you can take important decisions. So here, device to device or machine to machine communication, you can facilitate with the help of semantic web technologies. So within that, we have XML, RDF, OWL. So these are the semantic web technologies that basically help you to arrange the data that available in the World Wide Web. That is a vague data that is distributed vastly, and you have to bring out the important information from the data. Okay, so how Watson computer IBM has developed as an intelligence. So they basically use the semantic web technology at the back end. So it can just arrange those particular words that is required to fetch from the World Wide Web. And that basically facilitated by RDF and OWL. They are basically creating the ontologies. They are providing you the vocabularies. So nowadays, semantic web is used by Google, Microsoft, every companies. And to query those particular data, you have a SparkQL protocol or query language through which you can extract the information from the available World Wide Web data. So I have used these technologies for my implementations in past related to one project in IoT domain, and some of my research also aligned towards it. So I'll discuss in the next session most of the technologies that I've used for IoT implementations. Thank you very much for patient for listening. If anyone has any queries, you can please ask. Thank you.
Thank you, sir, for the wonderful session. I request all the participants to rejoin at 3:20 p.m. Thank you.